Okay, today's topic is atoms, but I divide atoms into two or three different sections depending on what part of an atom we're talking about. And so today we're going to start with the questions I have under the heading of atomic structure and theory. So that specifically has to do with atomic theory historically, like the theories of what an atom looks like, and then also is very specifically electron structure, electron configuration, and things like bright line spectra. So that'll be the first video. And then we're going to go into atoms in reference to bonding and stuff off of the periodic table and periodic trends. So I'm going to work from the January 2025 exam today because it has a lot of questions. As you can see, these two topics combined, this first video will be 7 points, and then the second one's 13 points. They went pretty heavy on it in January 2025, so I think it's a good exam to start with. So let's jump right in. Starting with question one, I'll tell you right now when you're examining the structure of the exam, the first 2 to 3, and sometimes even the 4 questions are related to atomic structure, particularly atomic theory. And then you'll see that repeat on the second part of the multiple choice section. So sometimes they do it, they're starting to not do it as much, but let's see what we get. So first question, we're going to do questions 1, 2, 3, and 4 first, and then I'm going to move to the other sections. So I'm going to time index. This one will be indexed by question, this video. First question, the subatomic particles in the nucleus of an oxygen atom. So a couple of key words that we've talked about before, which would be what are subatomic particles? You need to know that subatomic particles are protons, neutrons, and electrons. And you also need to know that those, which ones are located in the nucleus and which ones are outside of the nucleus. You need to know things like roughly what are their mass and what are their charge. So since they're particularly referencing the nucleus, you should know that protons and neutrons are the only particles in the nucleus. So that knocks out electrons, and it knocks out basically any choice with electrons in it. That leaves us to neutrons only and protons and neutrons. You should know that both protons and neutrons are in there. So at the end of this video, I'm going to quickly show you the study guides that go with atomic theory and structure, and I will go ahead and link those in the description. All right, next question. Number 2, which phrase describes the charges and numbers of protons and electrons in an atom? Let's make this a little bigger. Okay. So this one we did go over in class. It's a tricky question because it's one of those longer questions where you have to break down 2 parts of the answers. So we're going to use that strategy here just so I can go over that strategy with you again. And what that strategy involves is first cover your answers. Let's put annotate on. It gives me a hard time. Okay. First, I want you to not look at the answers for a second. You need to describe the charges and numbers of protons and electrons in an atom. Okay, so that means before you start looking at choices, you need to first write down for yourself what are the charges on, let's do this with annotate. So we're going to do this 2 ways here. First, I'm going to cut this in half so I can interpret it. They throw everything at you at once, and I don't want to talk about everything at once because I'm afraid I'm going to get confused, right? So I'm going to say first the charges of protons and electrons. So let's do that in blue. A proton has a +1 charge, an electron has a -1 charge, right? Now I've got my charges. Then I'm going to look at the numbers in an atom. Okay, if I know by definition the particles in the protons and electrons in a neutral atom, that's an atom that does not have a charge overall. It does not have a net charge overall because its protons and its electrons are equal to each other. In other words, it is not an ion. Ions are charged particles that have lost or gained electrons, and that's how you're picking up a charge. So this is just a plain old atom, like you're looking at it on the periodic table. So let's do a specific example and see if that helps a little bit. So if I take a look at, say, lithium, lithium, when it's neutral, has an atomic number of 3, so it has 3 protons. That would mean if this was a neutral lithium atom, it does not have a charge yet. It hasn't bonded to anybody. He should have 3 electrons. Okay. So just remember those charges that are listed on the periodic table, they are not the charges an atom has all the time. They are the possible charges an atom can pick up if it's in a compound. So this might be an issue with the way I teach it, but so now I know 2 things. I've got in blue here, protons have a positive charge and electrons have a negative charge. And I've got lithium has 3 protons and should have 3 electrons. So let's now divide our answers into 2 pieces. And remember that we're going to divide them at the point where each answer says end. So the first thing I'm going to do is figure out what's going on in this first section of each one. I don't care what the second section means because I'm going to first eliminate at least 2 of these based off of whether or not the first half of the answer is true. So do they have opposite charges? Yes, they do. So 1 and 2 are correct, but do they have the same charge? No, that means 3 and 4 are wrong. So this just knocked out this whole section. I don't have to look at this again for the rest of the question. Okay, this just should help you narrow things down and reduce your level of confusion. Now I'm going to address this second half of the question after the end. Are they equal in number or are they unequal in number? Well, we established that if this is a neutral atom, which they actually didn't mention, but it's an atom, it's not an ion. Okay, the difference between having a charge and not having a charge is being an atom or being an ion. So in this case, I should have equal numbers of protons and electrons. So the answer is choice 1. Okay, so this strategy of breaking these confusing questions down where they try to ask you about 2 things at once, you don't have to answer them that way. Do just 1 thing at a time because it's going to be better for you and you're going to be more likely to get the answer. All right. Number 3, the wave mechanical model is an atomic theory. There are multiple historical atomic theories, starting all the way back with Dalton's hard sphere. So I'm going to show you a review sheet that summarizes all of those. The wave mechanical model, sometimes now also called the electron cloud model, is the most recent atomic theory and the one that we have the most evidence to support is completely correct. Some of the earlier theories, however, did contribute to our overall understanding of what an atom is like and how it behaves. So that accumulates over time. And that's why you need the review sheet to kind of look at each one. The other question they love to ask in this section is what was the result of Rutherford's gold foil experiment? And that's why all that stuff is on the review sheet for you. Okay, so we're talking wave mechanical model. Wave mechanical model has electrons moving in clouds and also in orbitals. So which term identifies the region in an atom of lithium that is the most probable location of electrons in the ground state? So you need to know that this is a region in an atom of lithium that is the most probable location of electrons is the definition of an orbital. Okay. If we talk about the other answers that are here that we could have eliminated, first of all, the words hard sphere make no sense. This is Dalton's theory of an atom, but since they asked you specifically what's the most probable location of electrons, during the time that this theory they came up with the theory of the hard sphere, Dalton's theory, they had no concept of what electrons were even. This is about bonding, and we're not bonding these atoms. We're just talking about their electrons where they are, so that's wrong. And spectrum is related to this. However, we're not talking about electrons getting excited and changing energy levels and giving off light, so it's not this one. Okay, so orbital is a pretty popular definition to come up on the regions. It's a good one to make sure you have at your fingertips. Oh, keep forgetting that. turn off annotate to change things. All right. Now, this is actually an isotope definition, and technically I put this with the topic of nuclear chemistry. A lot of people teach it uh, all together, everything about atoms together, but I try to keep the stuff divided up to where it's used so it makes more sense, right? Isotopes are different versions of atoms that can be stable, can be unstable, but generally speaking, they have different masses because they have different numbers of neutrons. So it's important when you're looking at this, we went over this one in class also, that you review isotope notation because you need to know what this means, C12 and C13. And if you don't know what it means or you keep forgetting it, you have a fluency problem or a misunderstanding. And then that means you're going to not be able to do the application for this, which is what's the application of knowing what this number means and what you can do with it and what you can't do with it. So I'm going to, again, put those review sheets in the description for you. But there is a breakdown of this on the atomic structure review sheet. And there is a breakdown of this on the very short visual review sheet. So I'm actually going to go over those review sheets quickly at the end of this video. So if you don't want to watch that part, I'll have it indexed, you can skip it. But I definitely want to show you the visual one that I have made because it might be, if you're really struggling and you could just get this down, you'll get a lot of questions right. So this is generally also without looking at the specifics. In other words, the specifics in a question are they brought up carbon 12 and carbon 13. Those are specific isotopes. If I cut out this whole beginning of this question, right? Remember, this was the question where they brought up ground state like 10 million times and it was not even necessary to answer the question. What they really asked you for, actually, I'm just going to erase this. What they really brought up for you here is they said the word defined, which means they want a definition. They want a definition of an isotope. Doesn't even matter if it's carbon. The definition of an isotope is always the same. It doesn't matter what atoms we have. So according to the definition of an isotope, atoms that are isotopes, they give you half the definition, have the same number of protons. They just want to know what's different about them. So they have a different number of neutrons. End of discussion. This is also a critical key definition you must know. Sometimes they make you write this definition out on part 2 questions. And when they do that, they often now are very specific in saying that you must talk about the protons and the neutrons in your answer. So if you just say it has a different number of neutrons, or you just say it has the same number of protons, they won't take the answer because it specifies you have to talk about both particles. So they'll say that famous phrase in terms of protons and neutrons means you better talk about both of them in your answer. You're not going to get the point. Okay. So please, please, please be careful about that. So these definitions come up whether we do multiple choice questions or don't do multiple choice questions. So it's a good time to review all around. All right, let's go on to question 31 is the next time we're going to see stuff about atomic structure. So you're going to watch as I scroll through. I'm using the large type one, so there's not many questions on each page. When I get to section B1, the multiple choice essentially sort of starts over again. And a lot of times these first questions, so if you're looking to do one topic at a time, which is a strategy I recommend when you're doing the regions, is go to topics that you know you're going to get your core points on, then go back and spend time on the ones you're not as sure about, or that you're going to take a long time with a reference table or something like that. And I mean do all of them for that topic. The way I have it organized on the topic list, just do the multiple choice, then go do the part 2s, then loop back for the next topic you want to work on. I know this is unnatural. You guys want to sit and take a test and just do number 1 and then number 2 and then number 3. The issue with that is it's going to cause issues for you in terms of relaxing and remembering the material by topic. So I really strongly recommend that you do this one topic at a time. All right, so given the bright line spectrum, so how do I know that this is the topic of atomic theory and structure? Now we're talking about bright line spectrum. Bright line spectra are directly related to the where electrons are on an atom, right? What energy levels they are in. That is considered part of the atom's structure, the way it is put together. Okay. So bright line spectra are produced specifically because atoms have electrons that are in different locations. Since every atom's atomic number goes up by 1 as you move across the table, every time you get another proton, you get another electron, which means you have another electron that's in a different position than somebody else. So that is what's making each of their atomic spectra unique. So given these bright line spectra, now these, you don't even have to understand everything I just said. Bright line spectras with diagrams like this, they're matching games. That's what they are. They're just a matching game, right? So don't freak out. All I have to do is match stuff up. Now, one thing that I have to make very, very clear is that the matching can be difficult. So this is one of those times you're going to want to get a piece of scrap paper out and make sure that these things really line up. The second thing is, in order for an element to be present in a mixture, and you have 4 different mixtures to pick from here, every line for that element must be present in the mixture and it must be identical. In other words, it can't be possible that that line is being caused from a different element, right? So this line right here, if I line it up, it's missing from this one. See, it's completely not there. That immediately gets rid of mixture A, right? So we don't even want to talk about that anymore. I'm going to change colors. All right, now I go and I track this next line. If you look carefully, like if I had held a piece of paper up to this on the exam booklet, you will notice that this one, I've already eliminated it, first of all, because it was missing this line. It's also not actually lined up. If you look carefully, you can see it's actually a little bit to the right. The one that's lining up is this one, okay? And then remember, these are mixtures. I'm just looking for this element in this mixture. So this line also lines up with this one. Okay, there's something else in this mixture, but it's not element X. I'm just checking to see if element X is there. So I now have to, I'm pretty sure that this is probably, element X is probably inside mixture B, but I want to check some other things. So element X has a line here, which it matches up with this one. That line again is not present here. So if I line my piece of paper up, I'll see there's an empty space here. That immediately eliminates mixture C. Okay, and then again, element X. Now down here for mixture D, it's a little confusing. Some of these lines look like they could line up. So I'm going to move a little further out. And again, if I held a piece of paper up against this, I would see these two are matching. This one's actually not matching. If I held a piece of paper up to this, I would see that this one again is not directly underneath. It's actually off to the right a little bit. And so it's that fussy. It's that, in British lingo, we would call this fiddly. Like it's very specific. So if these lines, I'm going to erase for a sec. If these lines are not exactly represented in the diagram you are looking at, or if any, even one of them is missing, it is not in that mixture. Okay, these are, this element for it to be present, his whole spectra has to be there. So it is also very fussy. You have to hold a piece of paper to it and make sure that it really lines up. This is another good reason to bring a ruler with you to the regions. Okay, so which one contains mixture X? This is B. Now, this was also on the final exam, and so you may have gone over it already because you did it in your error analysis, so you might want to skip this question. All right, we are going now to question 51. So see, I'm going to skip to the part 2s because I want to do all the questions for this entire topic before I move on to the other atomic structure topic. Okay, so number 51 is about how bright line spectra are produced. So let's talk about this lingo. What kind of language are they using in this question that we have to watch out for? So first of all, they said state, which means you're not going to explain anything. Don't explain anything. right? You're just going to tell them. They already know, they just want you to see if you know. Then the next important phrase is, here it is, you guys, I just mentioned it before, in terms of electrons and energy states. That means I have to talk about both of those things in my answer. And so this is where those earlier strategies, unfortunately, that were taught to you in English classes, like restate the question, not going to help you because they're not interested in you restating the question. They're interested in you getting straight to the point. That's what state means. And they want you to be able to talk about both of these things, okay, in terms of electrons and energy states. How do atoms emit? If you haven't gotten this vocabulary down, it means give off. Okay, they make light, right? When you turn a light bulb on and it glows, those are the atoms in the light bulb making it glow because you cranked electricity into them and gave them energy. And then their electrons get excited, and when they drop back down, they're going to give that energy back to you as light. So what you're doing when you turn the lights on in your house is you're converting electrical energy into light. And to be honest, you're not doing it. The atoms in the materials your lights are made of are doing it for you. All right, so how is light emitted? It doesn't actually matter either that this is a boron atom, because this is what happens no matter what atom you're dealing with. So again, you don't have to mention anything specific about boron. So if you restate the question and then talk about boron, you're wasting time. So let's just talk about how is light emitted when an atom is given energy. So they want us to make sure we say what's happening to the electrons, and they want us to make sure that we say what's happening to the energy state. Okay, they did mention that, you know what, I will erase that part. They mentioned that it's an excited atom. So I will go ahead and say, let's not talk about that as boron because it's any excited atom. At what point, when electrons move up a level and then come back down, do they actually give off the light? Well, when they're moving up a level, they're not giving off light. They're absorbing the energy you gave them. It's when they come back down that they give the energy back to you as light. So if I were to construct an answer to this question, I would say, okay, so notice that I have very specifically mentioned the word electrons and I mentioned energy levels. I specified that I was going from a higher energy level to the ground state, which is kind of like a normal energy level for an atom. It's like where they would keep their electrons if nobody gave them any energy. Okay, sorry, that got a little bit rambled. I am reusing their word emit, and I am reusing these terms, but I am demonstrating to them that I know because I'm telling them I'm going from a higher energy level to a ground state level. If you wanted to borrow more of their language, you could say that the electrons are moving from the excited state to the ground state, and that would help you out a little bit more. Okay, so you are borrowing terms from the question. You're just not bothering with restating the question. You're just getting straight to the point. Okay, but you are making sure that you cover all the terms that are brought up in the in terms of section. So in terms of very specifically says, what are you supposed to be talking about? Okay. Um, this is actually, we're done with all the questions for this section. So I do want to take a quick jump over to the answer key because I want to show you how to look at a part 2 question again and see So we're on question 51. We are on January of 2025 right now. I want to look at the rating guide really quick because this is how you would check your answers if you were by yourself. And in the rating guide, what did they put for 51? And how could I see if my answer is right if I'm practicing this by myself? So let's take a look at whether or not. Now, this is one that's a little open-ended. It says acceptable responses include, and here's 4 suggestions for things that I could use to figure out if I will take an answer from a student, but it's not limited to that. All right. So notice that the most low, this is like the least wordy answer. Honestly, it would be great if you could get to a point where you are giving the least wordy answer, but notice that in every single one of these, they absolutely made sure that they used the words electrons, they used excited and higher and lower energy states because the questions specify they have to talk about both of those things. So if you're looking at your answer when you're practicing by yourself and you didn't talk about the electrons or you didn't say anything about the energy levels, the states, the energy states of low or high energy states, you're probably not getting the question right. Because even in their most short answer, they made sure to both use the term electrons and something about energy states, because in the question it said you have to. Okay, now they also specified excited, meaning that they were at a higher energy level, and then they specified they were moving to a lower energy level. So ultimately, your goal is to be get straight to the point. That means to be concise, is to be as concise as this without leaving anything out. But if you still need to kind of make sure you talk a little bit more about it because you feel like you're going to lose something, go with a longer answer. Just don't forget to do those in terms of. All right, so at this point, I'm going to move you over to the review sheets because I want to show you what review sheets are available, and I'm going to link all of these in the description for atomic theory because atomic theory is a big topic. It can be pretty popular on the Regents. And I want to make sure that you have all of this. So we are going to go to the drive. When did we do atomic theory? Quarter 3. We do atomic theory really late. So the review sheets are here. There's actually quite a lot of review sheets here. The first one I want to talk about is the atoms visual guide. So this visual guide goes over visual representations of atomic structure. It is really best, not everybody, it turns out there's really no such thing as a visual learner, but it helps a lot if you have a picture of this in your head. So I have a lot of kids who don't have a picture of this in their head, and for that reason, they keep telling me that electrons are in the nucleus. They are not. Okay, the nucleus is right here in the middle, and it's not held together by anything like on the outside. In other words, in a lot of diagrams, I'll draw like a circle around it, like as if there's a cell membrane holding them together. There's not any such thing. Okay, they are holding onto each other like pieces of candy stuck together. I always think of like if gumballs got all shoved together and stuck to each other. And then outside, orbiting this, are the electrons. Now, I say the word orbit very loosely. When people first started to try and figure out where these electrons were, they had kind of a romantic idea of how nature worked. And so they wanted everything in nature to sort of follow the same universal patterns because that had like a beautiful symmetry to it. And turned out it was wrong. But it's not always 100% wrong. So they don't go around in perfect circles like planets. Some electrons do go around in circles, and some electrons do some other really weird, funky things. So I'm drawing this with a very small atom, so just to give you a loose picture to have in your head. This is not really what an atom looks like, but this model at least gives you a sense of that the neutrons and the protons are quite large compared to electrons, which I draw much smaller. The charges are indicated here. Protons and protons have a positive charge, neutrons have no charge, there's nothing there. and electrons have a little minus sign next to them. I should annotate. I have a little minus sign next to them. Those guys, that's indicating it has a negative charge. Now, I wish that I had gotten this drawing a little bit better, but my protons and my neutrons should be roughly the same size. That's mostly just to make sure you have an image in your head, an approximate model that lets you know that they have the same mass. Okay, each of them has a mass of 1 atomic mass unit, which is abbreviated by the letter U. Okay, so this is a rough diagram. It's not actually very accurate. It's just to give you a picture to hang on to help you to remember what's going on. Okay, so subatomic particles are all the particles that make up an atom, protons, neutrons, and electrons. See in this little bubble, it reviews subatomic particles. And then what else? It defines mass number for you, which is in isotope notation, that would be this top number. That top number represents the mass, which again, it says here and here is the protons plus the neutrons. Okay, and if an atom is neutral, it is not an ion, and all its electrons are in their ground states. Okay, so a neutral atom, usually in Regents questions, all right, I'll be honest with you, this review sheet was made specifically with getting you through Regents questions in mind. So it's not always 100% accurate in terms of the chemistry. What matters is what you have in your head when you're tackling a question. Here are your particle counts in this neutral atom. You've got 3 protons that identifies this as lithium. That's echoed in the nuclear symbol. This nuclear symbol tells me everything that's in the nucleus. Right here it is, nuclear symbol. Then it has 3 neutrons. That's just a coincidence. They don't have to be, neutrons and protons do not have to be equal to each other. In this case, they are, and in some atoms they are. That's pretty stable, but it doesn't mean that you can always assume that the neutron and proton numbers are equal. The ones you can assume are going to be equal are the electrons and the protons. So this is confusing. The electrons and the protons being equal means that I have an equal number of positive and negative charges, which is what's making my atom neutral. Neutral means something doesn't have an overall electrical charge. When that happens, it means its charges are balanced out. Things pick up electrical charges in kind of a magnet way. They become sort of magnetic if their charges are not balanced out. You have positive charge somewhere and negative charge somewhere else. Okay? And so also I remind you over here that atomic identity is based on atomic number. All right, now down here, I contrast for you. I sort of compare and contrast what's the difference between an ion and an isotope. So up on the top, you kind of have a neutral atom. And then down here, I talk to you about what would make lithium an ion. Okay, to make lithium an ion, and my neutrons are sort of hidden behind my protons here. That's why you're not seeing them as full circles. You're going to notice in this diagram, this one has 2 electrons, and you'll see it down on my little table, versus my neutral atom, which had 3 electrons, 1, 2, 3. Oops. All right. So down here, I remind you of a few things. Remember, metals lose electrons, while nonmetals tend to gain electrons. Tend means most of the time that you're going to see them at your level of chemistry, they will have gained electrons and picked up a negative charge. Not always, but in a lot of cases. Positive ions are called cations. So if they use the word cation, it's cation, not cation. That means you lost electrons. Negative ions are anions. So in these little tables, what I'm showing you is how are the subatomic particles changing when I'm dealing with these different definitions. In an ion, the subatomic particle that's changing is my electron number. In an isotope, my subatomic number that's changing is my neutron number. Okay, so here you're going to see he has the same number of electrons as it did over here, but it's my neutron number that's changing. So lithium can have a different number of neutrons. In fact, there's a couple of different isotopes of lithium. So this is lithium 7. which is an isotope that has 4 neutrons instead of 3 neutrons. This is what I meant by saying you can't just assume that lithium has the same number of neutrons and protons, the way you can assume that a neutral lithium atom has the same number of electrons and protons. So you're going to want to really get that straight in your head. Right? So this table shows you that in order to make this an isotope, it's the neutron number that must change. In order to make an ion, it's the electron number that must change. And down here, I show you the math of how you pick up different charges. Now, lithium does not become an anion, it doesn't gain electrons, but I showed you an example of how its charge would change if it did pick up an electron, because I just wanted to show you an example of what that looks like. Right? So notice that in all 3 of my tables, what has never changed is my number of protons. And it can't really change because this atom is lithium, and what identifies it as lithium is its atomic number. All atoms of lithium must have 3 protons. Otherwise, it's not lithium, it's something else. Okay, that's a really important point that we have to make sure we nail home. All right, and I'm not going to go over it fully, but I am going to show you the study guide for atomic structure. Again, it'll be linked in the description to help you get to it quickly. This is a kind of crash course on all of atomic structure. And again, it goes through that same exact stuff that's depicted in the pictures in the other review sheet, but it's all just written out for you and it's organized into a table. Which subatomic particle are we talking about? Where is it in an atom? Its location. Nucleus, nucleus, not in the nucleus. What is its mass? Okay, remember electrons have almost no mass. What is its charge? Remember neutrons don't have a charge. And it goes over what is mass number, what is atomic mass, what is charge, what's the charge on the nucleus only. If it asks you about the charge on the nucleus or the nuclear charge, they don't want to know about the electrons, they just want to know about the protons in the nucleus. What makes an atom neutral? And this is a table showing you again how ions get their different charges, but in this time it's not all written out in pictures for you. I show it to you as a table. So I just wanted to offer it to you in a bunch of different formats so that whichever format works better for you, you can use that review sheet. So here's a review of isotopes. Here's a review of all the different types of isotope notation. Okay, you have to recognize all of these 3 different types of notation and what it means and what that number means and where it will be, right? So there's a big explanation here of isotope notation. Here's a brief rundown of all the atomic theories and what they found. Okay, so here's the theory. Here's what was correct and the important finding they expect you to know on the reagents. I will tell you right now, they're real fond of the Rutherford theory, which is they'll often talk about the gold foil experiment. They are often very, once in a while, they'll bring up Thomson. Remember, J.J. Thomson is the one who discovered that electrons are negative using cathode ray experiment. He also was famous for the plum pudding model, which wasn't correct. And then everything here comes under quantum mechanical theory, which is wave mechanical theory and electron cloud theory. You do not need to know all of these names. Bohr, Bohr you should know, but Heisenberg, Pauli, Hund, Aufbau. This is just me getting into it in case. This is how many electrons are in each principal energy level, how many maximum they can have, and how to write excited states. And here's a little rundown again of how to read bright line spectra. So this is a very quick way to do this review without having to do the slideshows. All right, I'm going to end it there, and I will link those slideshows, link those review sheets for you in the description. The next video is going to be atoms bonding in the periodic table. See you there.